Hello, in this video I'm going to talk a little about power distribution at a national level. So in the UK, that's what we refer to as the national grid. It might be the same in other countries. So the national grid here is, it's both an organisation that is managing the power supply so that supply meets demand, but it's also used to refer to the actual infrastructure that we use, connecting the power stations through all these overhead power cables. Some of them are underground, but we have a lot of overhead power cables, and then going into whether it's heavy industry, light industry, into the home and such like, giving different voltage power supplies into different parts of the national infrastructure. So power supply is it was worked out pretty early on that it's much best to do this using alternating current rather than direct current. And the reason for this is we want to transfer power, we want to deliver this electricity at low current, because the more current we've got, the more the cables are going to heat up and the more energy we're going to lose. So remember with these things, our power I squared R for a particular cable. So if we've got an overhead power cable, if we can, the resistance isn't going to be changing. If we can reduce our current in the overhead power cable, then we're going to reduce the power dissipated in that cable. Now, the power supplied, of course, and this is the difference here. This is our power dissipated in a component of resistance R. The power that we're then supplying, of course, is the current multiplied by the voltage. So we want to supply a lot of power and we want to do it at low current. So we're going to need to do it at high voltage. We don't want to be sticking massively high voltages into people's homes or even into industry for that matter. So we need to have the ability to take some starting voltage, ramp it up to a really high voltage, and then drop it back down again so we can use it at the other end. It's much easier to change the voltage of alternating current because we got transformers and we can use electromagnetic induction. We don't have that luxury with direct current. So if you're trying to distribute energy using direct current, you tend to end up having higher currents and greater power losses, which just makes it just too inefficient. So that's why we've got alternating current as our power supply. And this is the case everywhere. This isn't just a UK thing. This is the reality of distributing electricity. So we start off, we've got our power stations doing whatever they're doing. They can be generating this electricity in a load of range, loads of different ways. These could be wind turbines, it could be fossil fuels, it could be nuclear, anything. They're producing electricity, and they might be producing electricity as, I don't know, 25,000 volts, something like that. So it's already pretty high voltage, but we can get it much higher in order to distribute it through our power cables. So head that off to our first set of transformers and then stick it into the pylons on the overhead cables. So we might step this up here to 275 to 400 kilovolts. We're talking epically high voltages here as they shoot off along these overhead power lines. Then where we've got it closer to what we want, we can then start stepping it down again. So you might do an intermediate step down, taking it down to say 130 kilovolts, and then we're going to start separating it out for, well, what are we wanting to do with this? Because depending on whether we're wanting to use the electricity in industry or in the homes, domestic setting, we're going to want to have different voltages. So if we're in heavy industry, then it might get stepped down to maybe 30,000, something like that. So 30 kilovolts. These are all ballpark sort of figures. If we're going into light industry, then we might want 10 kilovolts. And then, of course, when we get into the home, then we're looking all the way down to, well, there's no, maybe about it is 230 volts we've currently got. It used to be 240. I think they're currently dropping it down think Europe uses 220. So we're sort of on that path of dropping things down to sort of standardize a bit more with what they use in other parts of the world. At the moment, we're at 230 volts for our alternating current, and that's 50 hertz is the frequency of the AC. So, when we've got our AC alternating with our voltage against time, the frequency of this oscillation here is at 50 hertz. So yeah, that's what we're doing with step up and step down, and we can only do all this with these transformers, which requires AC. Right, now we don't want to get confused about what these voltages actually mean, because I've seen people look at this equation here and say, oh yeah, well the power dissipated is I squared R, and then they'll say, oh yeah, but we can also write that as V squared over R, and look how high these voltages are, and we're still going to get this massive power loss. Well, of course, here you're not looking at the right thing if you're thinking about this formula here, because the voltage here, remember, this is power dissipated in a component. So, the component of resistance R, the power cable of a certain resistance, which we were saying in a previous video, might be something like 0.3 ohms per kilometer of overhead power cable. But the V here will be the potential difference between one end and the other end of the power cable, which is low. It's not this value. This is the difference between the cable that's going out and the cable that's coming back again. So, and we'll see this when we look at, let's look at home supply. So if we got 230 volt AC coming in, that means this cable, if this top one's our live cable, that's got a potential of 230 volts. If the bottom one is our neutral cable, that's got 0 volts. So the potential difference between these two wires is 230 volts. It's not the potential difference from one end of the wire to the other. And it's the same thing with the overhead power cables. The potential difference of 400 kilovolts is between wire out and wire back. The cable out and the cable back is not from one end of the cable to the other one, which is why this doesn't make sense if you start looking at this formula. But I've seen a lot of people get confused by that. But yeah, we've got this same setup in the home. Now in the UK, in homes, we have what's known as ring mains. My understanding is they don't have these everywhere in the world. I think we went for ring mains because of it's a historical thing, because of the copper shortage after the end of the Second World War. So we have two big cables that run around the house because it means we have to have less wiring in order to connect everything up. So I'll make the comparisons of what happens in the UK and apparently what happens in other parts of the world. So we'll have one, for say one floor in the house, say you're downstairs, or say you've just got a flat, you'll have one wire which goes all the way around the flat, which is our live cable. We'll have another one which is the neutral, which goes all the way around. And then every time there's a plug socket, we're putting in more or less an ability to plug in a component, some kind of device between these two cables. So this will be our plug socket with two of the pins. We have 3 pins on a plug in the UK. I'll get onto that in a minute. But 2 of these pins, the live and the neutral, will tap into these 2 wires, and they'll go off to some component, some device which we've now connected up to our AC supply. So this means you just have these 2 long cables that just run everywhere. I mean, the alternative is, you say for every socket that you want, you run a pair of cables. You might have, our supply comes in here, our 230 volts, you'll have some kind of fuse board, which is then every time we want to connect a socket somewhere, we'll run cable out from live and neutral to the socket. And then we can manage all of, a lot of what's going on and the fuses and such like all on the fuse board. This means you've got more cable going out and back all the time, because every time you've got a socket in the wall, you've got cable going out and back. We don't have that with a ring main, because we're just running one long wire all the way round. So you want to hook up another plug socket, well, you just stick it in. The wires are just there, ready to go. Providing it's adjacent to the two rings. So it uses less copper wire from that point of view. It does create other issues because then we have bigger plugs in the UK because we're then having to put a fuse in every plug, which makes them bigger and bulkier. Because now we're putting more of the responsibility on managing each appliance and each connection to the ring main. We've moved it away from this sort of centralized fuse board onto each individual socket. So things have changed a bit. The makeup of the plugs then, these big chunky plugs that we have in the UK, we've got 3 pins on them. So you get the live and the neutral. So if you open up the back on it, you've got the brown wire, that's our live wire, which is connecting to the 230 volt wire in the ring main. We've got the blue wire, which is the neutral wire, which is at 0 volts. So brown is at 230 volts, blue is at 0 volts. And then we've got the long pin, which is the sort of green yellow one. Although it can be a nightmare sometimes because they've changed these colours so many times. You can open up plugs that have just got all manner of weird blinking colours in them. You can get red ones, you can get stripy ones, you can get all manner of horrible things going on. But as far as I know, these are the standard colours nowadays. And that goes off to earth, the green yellow one. So that's also going off to 0 volts. You've got like a quick route down to that's how earth is represented on the circuit diagrams. You have a metal spike underneath the house. It's just like stuck in the earth, and it's giving us a quick escape route for current if something goes wrong. And then you'll have the fuse sitting in this as well. Inside the plug. I mean, the fuse is really there to protect the cable, so that goes off to the appliance rather than actually protecting the appliance itself. You don't want the cable melting or getting too hot or setting a light or whatever. This is why we have these big plugs kicking around over here. The fuse that you've got will depend upon the current. You get a different circuit. So although we have these ring mains, you'll get a separate ring for in the kitchen really, because that's where you've got your high power appliances. So you'll have thicker cables and bigger fuses because you'll have larger currents inside the kitchen appliances. Because of course our voltage is fixed. So if you've got high power appliances for a fixed voltage, then the current has to go up. So if you've got piddly little appliances, things like TVs, lamps, fridges, stuff like that, then you're looking at less than 700 watts. You're looking at 3 amp fuses in your plugs. If you've got the big hitters in the kitchen, the high power things, kettles, ovens, washing machines, toasters, things like that, so we're looking at things that are like 700 to 3000 watt appliances. Your big energy usage things, then you're looking at 13 amp fuses on your plugs because we've got much higher current. You can see we've got 4 times here, 700, multiply that by 4, you're getting near to 3000. So we need 4 times the current for the same voltage in order to have that sort of power. So you just need to be a bit more careful when you're then protecting all of those components and making sure things aren't going wrong. So there you go. That's just an overview of what's going on with electricity distribution, with an emphasis on what's happening here in the UK, just because that's where I am. Hopefully that's been helpful.